So, we have been looking at divide and conquer algorithms and merge sort, binary search, matrix multiplication, integer multiplication, maximum, contiguous sum, whole bunch of problems. And often we needed to solve recurrence relations to analyze these algorithms. So, just to it will be nice to have some general, have solution to general recurrence relation handy, so that we don't have to expand and solve every time. So, let us try and look at this recurrence relation. And try and find solution for this, because this sort of recurrence relation will keep coming in many problems. So, here, so T of 1 would be, or we will have some boundary condition, some constant C, which, and so we have A is greater than 0, B is greater than 1, and D is greater than equal to 0. Right? B is 1 does not tell you anything, because T of n, you are writing it in terms of T of n again, so that is not useful. So, B is at least 1. So, this is the kind of recurrence relation we will come across, and so it's nice to solve and be able to plug in values for A, B and D and see the solution instantly. It will be very useful for that. Okay. And this is not it's not going to cover every recurrence relation you are going to come across, but this will cover most of the problems we will handle, most of recurrence and analysis of most of our algorithms. So, we will solve this the way we have been solving recurrence relation, by just expanding it. The main thing is we want to find the closed form for this based on A, B and D, so that whenever we come across such a recurrence relation for a different algorithm, we know immediately what the solution is. Okay. So, strictly speaking, T is defined for integers, so I should say ceiling or floor or something, but for our purpose, as we have been doing, we will assume n is power of b, so that not just n by b, n by b square, n by b cubed, all of them will be integers. Okay, and it's not a serious assumption. We went through this for merge sort, that even with ceiling, we actually analyzed the algorithm, and we did how to do that, and so we could do that and get a similar, and it's typically a constant factor of whatever you get if n is a power of b. So let's try and see what the solution is. So, let n be some power of k, power of b. So, when I expand it, I get T of n is so let's say this is some constant times n power d, and it may not be the same constant, it could be the same constant. You can pick the bigger of this and call it C, but let's this is not going to play a big role for me, so I'm going to say some f. Okay, so T of n is C times n power d plus A times what is T of n over b. We apply the same recurrence relation. So, it's C times n over b power d plus T of n over b squared. Right? No. I left something. Is this fine? So, this is C n power d, and I plugged A outside and I expanded T of n over B. Nothing missing? Yeah.
There will be another A.
Yeah, there's an A missing, right? C n by b whole power d plus A times T of n by b, which is n by b squared, right? So, this is C n power d plus C times A n by b whole power d plus A square times T of n over b square. So, okay. So, this is C n over d plus C A times n over b times t plus A square into, let's do one more time and then we'll start seeing a pattern. C n over b square whole power d plus A times So, one way to visualize this as in some sort of a tree form. So, we have T of n, which we write this as C times n power d plus A times T of n over b. Okay. So, A subproblems, you can think of it as A subproblems of size n over b each, which I am solving recursively. Okay. So, now if we expand this out, so each one of them would be C times n over b whole power d, and then this will have some A subproblems, this will have some A subproblems, this will have some A subproblems, and each one of them will be T of n over b squared. So, that is what is happening, right? Because you have A square times T of n over b square, because A into T n of b square, A, and there are A square times T of n over b square, so that will be this, and you have the C n power d here, and then there is a C n by b whole power d A times, okay, right, and you can keep expanding this. There will be some branching factor of A for each one of them. So, next time there will be A cubed T n over b cubed, and that is what we have, and this. So, can you say what will it be in general, or how long, what would be the height of this tree? K, because when you reach, eventually you will have at some point T of n over b power k, a power k times, and n over b power k is 1, and T of 1 is f. So, all of these guys will become f, right. So, how many f's will be there? So, at the end, because it will be a power k times T of n over b power k. So, this will, okay, so let's write this with the dot C n power d plus C A n by b whole power d plus C A square n by b square whole power d plus C A cubed n by b cubed whole power d plus dot dot dot, and it will be C A power k t of n by, oh, is there a C somewhere? Yes, I'm missing C, right? This doesn't have a C. At the end, you don't have a C. Okay. Yeah, I'm writing. So t of n by b power k, and this will become an f. Okay, so let me write the previous term. So this will be C a power k minus 1 n by b power k minus 1 whole power d plus, there is no C, a power k into t of n by b power k, which will be like t of 1, which will be f. Okay, so this is what it will turn out to be. Okay, I mean this is always a useful way to see how to solve recurrences, because you just write the term without the t, and then you have so many t terms, and each one you can keep expanding it, and eventually, you have to sum all these terms without the t, and that's what the sum is. Okay, so let's write this nicely and see what it is turning out to be. Okay, so I'm going to erase this. So this is summation C a power I into n by b power I whole power d right, I going from 1 to 0. I have to be a little careful, because when I plug in 0, okay, that's okay, right. So when I plug in 0, this goes away, this goes away, I'll still have n power d, so correct. Okay, 0 to k minus 1 plus a power k into some constant f. Okay. So what is a power k? K is log n to the base b, right? So a power k f. So this is, let's write this in a nice way. So I'm going to say C n power d into a power I b by p power I whole power d. Okay, what is a power k? A power, so f into a power log n to the base b. So what is this? This term is basically a power log n to the base a into log a to the base b. Okay, it's just the property of log. Log n to the base a is log n to the base b is log n to the base a times log a to the base b. So what is this? N. Does everyone see that? Because this is exactly the definition of anything power log n to the base that is n, because that's exactly the definition of log. So this is n power log a to the base b. Okay, so that's going to play a big role now. Let's see. I don't know whether I wrote this in a nice form the way I wanted it, but let's see. Okay. So now I want to compare D with various things and then take a call.
Sir, a to the power I by b to the power I, you have made whole power d, but it's only for d.
Good point. Very good. Yes. I know there's something I didn't do properly. Okay. So what I want to do is what I really want to do is this. Okay. So n power d is here. A by b power d power I. Okay. Is that okay? Thank you. Okay, so now let's look at the following cases. So k is like log n to the base b. So case 1, if d is equal to log a to the base b. See, a is greater than 0. Okay. Yes, okay. If d is equal to log a to the base b, what happens? So I don't know d, I don't know a, b, right? You are talking about some arbitrary problem where you have broken the problem into. Is there a problem? I can't hear you. Can you say something? Okay. So if d is equal to log a to the base b, so you have an arbitrary problem. I have divided the problem into a subproblems, each of size n by b, and then I have combined it using n power d times. Okay, that's how we have done. Now you can, we'll come back and see how we did for merge sort or binary search, and all of this will fall into this. Okay, so if d is equal to log a to the base b, what does that mean? A is equal to b power d. So that means that this term vanishes. This becomes 1. So you have c power n by d, c power c n power d, because log a to the base. So this is also d. So what would be the running time? T of n is big O of, yes, n to the power d. No, not just n to the power d. How many times it's appearing? K times. What is k? So it's n to the d log n, right? Because this is 1. So you have C power, so the overall runtime is C n power d into k. This is also n power d, so another 1, so k plus 1, but k is log n, so it's order n power d log n. Okay. If d is more than log a to the base b, that means, what does that mean? That this a by b power d, so b power d is less than a. So this is the ratio less than 1. Okay. So you have a geometric series because it starts with c n power d and the ratios are all decreasing, right? Then we saw that if you have a geometric series, right, like 1 plus 2 plus 2 square up to 2 power k, I told you a simple heuristic is that sum is essentially dominated by the last term. Okay, because this is increasing like this, and this last term is what it is. So you are here the last term would be c n power d into whatever this times k. Okay, but k is log n, so this is, it doesn't matter. It's still some n or something. No, some constant here. Okay, so I want to claim this t of n is order n power d. Let's see why. Is that clear? Okay, so this term is not really playing a role. I want to say that this is essentially c n power d.
If you take C and power D outside, that summation will converge.
Yes, exactly. Even if you take c n power d outside, this will be like the first term will be 1, second term would be plus some ratio less than 1. So think of it like half or 1/3. Even if you go all the way up to infinity, that this sum is going to be a constant. Right? Because a by b power d is less than 1. So take c n power d out, then you are summing something d power, don't use the d, some h power I, where h is less than 1. Okay, that's a convergence series, so that sums to a constant. So this gives you order n power d. Since d is greater than this, even this doesn't play a role, it's n power d. Right? Anyway, the running time is at least n power d because the combined part of it takes n power d. What this is saying is that d, so the key thing is to compare d and log a to the base b. That's all you should remember. Okay, so if d and log a to the b is base b and are the same, then you have a log n multiplicative factor. If d is larger than log a to the base b, then this dominates, and if d is smaller, then this will dominate. Because this is, so if d is smaller than n, so that means b power d is smaller than a. So this is an increasing term then. This is an increasing geometric series. It starts with c n power d. So a by b power d is larger than 1. So it is something like this. Some larger, some ratio which is sort of increasing. So you take the last term, and the last term is essentially this. Okay, so what is the last term here? We don't need this. The last term would be c n power d into a by b power d times log n to the base b, right? Because, which is exactly what I've written down here anyway. So I think this would be c n power d a times log n to the base b. B times log n to the base b would be n. That n power d and this n power d will cancel, and that's what you will have. And this is same as saying because a times log n to the a times log a to the base b. So overall it will be c n log a to the base b, and this is an f times. So overall it will be order n to the log a to the base b. Okay, so let me just summarize and write it down, and then we will verify on the problems we've already seen, right? So this is T of n is okay. Okay, so let's try binary search. So what is A, B, and D? You've just taken your problem, divided it into one problem of half the size after performing one comparison. So A is 1, B is 2, and D is 0 because you just spent constant time, right? Okay, so now let's see what log A to the base B would be 0 because it's log of 1 to whatever the base, and it's the same as D. So it falls into this case, so n power d times log n, so it's log n, okay, because d is 0. Merge sort would be A is 2, B is 2, and D is 1, right? Because we divided the problem into two subproblems of half the size, we recursively sorted them, so 2 and 2, and we merged them in linear time. Okay, so here again log A to the base B is 1, which is the same as D, so it falls into this case again, so it's n power d log n, which is n log n, right? So let's we looked at integer multiplication, which we saw last time. Not everybody was here last time, I think. So just to quickly recall what we did, we want to multiply two n-bit numbers. Okay, two n-bit numbers. We want to multiply them, and we want to count how many single-digit multiplications you are doing. Okay, the standard algorithm which you learnt in high school will take how much time? N square, because you will take this entire thing, multiply by this, and write it down here, and then entire thing multiply by this and write it down with the shift, and that's how you will write, and finally you will add them all, right? So there will be n multiplication with each digit, so that will be like n multiplication, n square, and then you're going to add them all, that's again another n square. So overall it's an n square algorithm. And we wanted to see if I want to apply divide and conquer, can I get something better, and how do I even apply divide and conquer? So the way we saw was, we looked at, so we take this two integers, let's call x and y, divide, so take the first half bits and call it an integer of size n by 2. This is the second half, this is the first half of this number, this is the second half of this number. Then we observed that xy is nothing but, so what is x? How do you write x? X is a times 2 power n by 2 plus b, right? Because if you think of a as a number of with n by 2 bits, because right, so if I think of, how do I write this number? It's 547 into 10 cubed plus 563, right? So it's a decimal number, so it's 10 cubed, but if you are talking about binary, it will be 2 power or something, right? So if you think of this whole number as a number with n by 2 digits, then xy, x is a into 2 power n by 2 plus b, y is c into 2 power n by 2 plus d. So xy you can write this as ac into 2 power n, right? Because it's a into 2 power n by 2 plus b. So it's plus bd plus ad plus bc times 2 power n by 2. Right? Because x is a times 2 power n by 2. So xy is ac times 2 power n plus bd plus a into d plus b into c times 2 power n by 2. So now if I recursively multiply these guys and do all the additions, what would be a recurrence relation for this algorithm? T of n would be how many multiplications of half the size? 4. You see that? This is 1, this is 1, this is 1, this is 1. So T of n would be 4 times T of n by 2. And then you are multiplying by 2 power n in the binary thing, it is just some shift. Then all these additions, because it's all going to be, some 2n bits numbers in the worst case. So in order n time, you are going to do these additions. Okay. Now let's come back and see what is the running time, because now we have this tool available. You can quickly plug it in and see what the running time is. So we come here and say A is 4, B is 2, and D is 1. And that comes to log a to the base b is 2, and that is dominating n power d, so it's n square, so it looks sophisticated, but we didn't improve the algorithm. Because remember our high school algorithm, we said it's n square anyway, so we didn't really do much, and so this gave an n square algorithm. But we know if I want to improve the algorithm, we know where to play the game. So, looking at A, B, and D, we know if we can do something better, and yes, we did something better. What did we do? We said, instead of writing xy like this, I'm going to now reduce it to not 4 but 3 n by 2 by n by 2 multiplications. I'll tell you how to do that. So it's AC into 2 power n plus BD plus A plus B into C plus D minus AC minus BD into 2 power n. Okay. So this is doing AC. I really want AD plus BC, but it's also doing AC and BD, so I'm subtracting it out. How many multiplications have we done? Well, this is 1, this is 2, this is 1, 3, because A plus B will be an n by 2 plus 1 digit at most. These are not new multiplications, I have already done that, so I subtract them out. So this 4 becomes 3. If I want another solution, just come here and look at it and say, hey, this is n power log a to the base b. So log 3 to the base 2, which is like 1.81, improving from n square. Okay. So having this tool is very helpful because moment you have an algorithm, you can look at it and know what the solution is. B, it also tells you where do I have to play the game to improve the algorithm, right? Okay. Then the other problem which we looked at was matrix multiplication. Where you had two n by n matrices and we want to get the product, the standard matrix multiplication. Okay. So the naive way of doing the matrix multiplication will take how much time? In cube time, because there are n square entries you are computing here, and each entry takes you have to take one row and one column and multiply them. That's like a n multiplication. So that's like n cubed, n multiplications, n minus 1 additions. So for each entry in the n square product you are computing, you are spending linear time. So that gives you an n cubed running time. And we said let's try divide and conquer. Okay, because that seems to be the fashion to do it. How did we do? Again, we divide these two matrices into n by 2 by n by 2 matrices each. So let's call this A11, A12, A21, A22, B11, B12, B21, B22. Then we said, okay, now the standard way of multiplying would be A11, B11 plus A12, B21. We'll put it here and so on and so forth. So each one is a multiplication of two n by 2 by n by 2 matrices. How many multiplications will you do? Right. So this would be like A11, B11 plus A12, B21. That's going to be the first term. And there will be another term here, another term here. So that will be 8 multiplications of half the size each. So my A would be 8, B would be 2, and putting things together, all these additions, because it's all n square terms, will be like an n square times, so D will be 2. And what would be the running time? N cubed, because it's log A to the base B, so that's n cubed, didn't really save from the standard n cubed multiplication. However, a guy named Strassen long ago came up with a way to multiply two 2 by 2 matrices using not 8 multiplications but 7 multiplications with a lot of additions, but still something small. And now if you apply that recursively, you get an algorithm whose running time is n power 7 to the base 2, which is better than 3, right, which is 2.81. Okay, it's good. So divide and conquer is generally useful, and way to analyze divide and conquer algorithms is using recurrence relations, and having a solution to this kind of a recurrence relation is pretty handy because you can just look at whatever A, B, D and plug it in and get the solution. Okay. All right. So let's look at a problem where we will use recurrence relation to guide our algorithm. Okay. All right. So the problem we want to solve is we want to find the median of a given list of n numbers. So this integer multiplication, I showed you an algorithm which is n power log 3 to the base 2 using that cute trick of reducing from 4 to 3. We will actually further improve it, okay, to actually get an n log n algorithm next time. But today I'm going to talk about finding the median. So I said early on that I keep saying my input is a list of numbers, but it could be just anything totally ordered set where I'm able to relate to if this is less than that, that's greater than that kind of thing. So for convenience, let's assume it's numbers. So what is median? Median is that element that appears in the middle of your sorted array. Okay. So if n is odd, you know what middle is well defined. If n is even, there are two candidates, just pick the smaller one, let's say by convention. Okay. So we want to find how much time or how many comparisons do you need to find the median of a list of n numbers. Okay. So what algorithms do we know naively? Yeah. Yes. So one algorithm we know is we can sort the entire list and pick the middle element. How much time does it take? N log n, because at least we saw one algorithm merge sort which takes n log n time to sort, right? But it seems to be doing more than what I really need. I suppose I care only about what appears in the middle. Can you do better than sorting? Okay. It was an interesting question. In 70s, several people joined together and actually came up with a linear time algorithm, okay, using divide and conquer. So if I want to use divide and conquer, let's see what kind of recurrence do I want if I want a linear time. Okay. So let's say, okay, and as always, it's so clearly if I want, let's say if I want the 10th smallest element, can I do it in linear time? How do I do?
Just find the minimum, the second minimum.
Yes, keep finding the minimum. So minimum you can do in linear time, and then second minimum. In fact, I've given you an exercise which tells you can find the second minimum in n plus. You don't need another n, but some little of n. But anyway, so you can keep finding the minimum. If you want the 10th smallest element in 10n comparisons, in the worst case, you can actually find the 10th smallest. So the problem is I want something in the middle, and so that's like a median, n by 2th element. So if I just apply that, that's like an n square. Okay. So as is always the case in recursive algorithms, we will actually generalize this, and we will talk about find the kth smallest element for k, general k, any k in linear time, right? Small k we know how to do it in linear time. We'll argue you can find in linear time. Okay. So if I want a linear time algorithm, what sort of a recurrence do I want? Maybe we should play around more with these recurrences. Let's see. Yeah. Okay. Before I do that, let's try and get the hang of. Suppose it is T of n is what do you think this will solve to? Of course, you can look up and tell me, but you want to make a guess first? Logarithm, log n. Okay. Okay. So there's one guess says log n.
8 instead of 1.
Okay, so argument is the same as sort of like binary search, except instead of 7. So in binary search, what would we have? We had t of n by 2 plus 1, which we know is log n. So what I have here is instead of 2, remember b is whatever is in the denominator. Okay, so instead of 2, I have something slightly larger than 1, and a is 1 anyway. So as long as I have slightly, so log, because all I care about is log a to the base b, right? D for us is a constant. So log a to the base b, and a is 1. So as long, if this is 1, then this will be 1. Okay, then d and no, d is still constant, so which is fine, which then this will start, it will be like n linear. But if b is larger than 1, this log a to the base b will be 0, because log 1 to any base is 0. So this is 0 and that is 0, so the both will be log n, because n, this is a constant, so d is 0, and if b is slightly larger than 1, then it is log a to the base b is 0, so it's binary search. So what have we done? In one step, we have thrown away a fraction of elements. If you manage to do that, you get logarithmic time. So that's the way to remember, right? I'm just spending, binary search actually threw half the elements, but what this is saying is you don't need half. Even if you throw away 1 by 100 elements, it's still binary search, because again, the way we solved this recurrence relation, if you expand it and see this geometric series coming, you will see that it's log n. Okay, so what about T of n is seven n by 8 plus order n. Order n. I mean, you can plug it in and see, right? Again, log a to the base b for us is 0, because a is 1 and b is a number bigger than 1. So log a to the base b is 0, but the other guy is 1. So that is dominating, so that will be the solution, right? So it will be linear. Okay, so I mean, you could just go and play around with this recurrence and see, you get a hang of it, then you know. So what is this? This is saying that in one step, if I throw a fraction of the elements, then I get logarithmic time. And this is saying in linear time, if I manage to throw away a fraction of elements, overall running time is linear. Okay, so if I want a linear time algorithm for finding the median or the kth smallest element, one strategy is somehow look at your input, pre-process it, and in some linear time, you manage to throw away a fraction of elements and then recurse on the remaining elements, then you are in shape. Right? So how do I even get to throw away elements if I am looking for kth smallest element? Okay, let's see. How can I throw away elements? What makes me throw away elements? So here is a strategy. So I have my entire list of this big array of n numbers, and I just make a guess and say, okay, I pick some element, some random element. In fact, random is very useful, but let's say I pick an arbitrary element. Step 1, compare all elements with x. Okay, and let's even assume that all the numbers are distinct. It just makes life easier. And partition my list L into L less than X, X, and L greater than X. Okay, I picked some arbitrary element. Compare every element with that. How much time have I spent? Linear time, n minus 1 comparisons. And then I say, I look at how many are less than X, how many are greater than X. I can count these numbers and then just partition. Within here, I am not doing any comparisons. I am not keeping it in any particular order. I just do this partitioning. And let's, okay, so now what is the really lucky case if the number of elements less than X is exactly K minus 1. Remember, I am looking for kth smallest element, right? So the number of elements, I picked X, compared with everybody and found that exactly K minus 1 elements are less than X. Then what? X is the answer. That's, the most lucky case. Then return X. Suppose this is greater than K. So I am looking for 20th element and it turns out all those less than X, there are some 100 of them. So I can get to throw away some elements. Which elements? I can throw away all those guys because look, I am looking for 20th smallest element. I picked some arbitrary X, did my comparison, and it turned out there are 100 elements here, and the remaining, let's say, some 499 elements or something. There are 600 elements. Then the 20th element I am looking for, 20th smallest element must only be here. So what is the point? I can just throw this away and recurse. Right? Else, that means that this is much smaller than K minus 1. I am looking for a 20th smallest element. The X I picked turned out to be the 7th smallest element by doing this count. Then what do I have to do? Recursively, I look into this list for what now? Not K. I am not looking for Kth smallest now. K minus whatever I have picked here. Right? Else recurse in L greater than X for K minus whatever the size of X minus 1 element. Okay. So I asked the question, how do I manage to throw away elements? Here it is. In linear time, I spent linear time by doing this comparison. I managed to throw away some number of elements. Okay. But I may be very unlucky that I might throw away one element for all you know. I'm not done much, right? When will that happen? Right. So I'm looking for kth smallest element, and it turned out my X was the smallest element. Suppose my X happened to be the smallest element, there is nothing here, and my element I'm looking for is here, so I've just managed to throw away one element. Okay, that's really the bad case. Okay, so if this is my algorithm, in the worst case, what would be my recurrence for a worst case? T of n. I spent some n minus 1 comparisons in this step, and I may be very unlucky and I just got to throw away one element, and this would be a bad case, right? What does this solve to? Okay, this doesn't fit into our the theorem we wrote, but you can keep expanding it. N minus 1 plus n minus 2 plus n minus 3 will be like n square. So not a great algorithm as such, the way I've just stated it. but I told you how to throw away. So if I am very careful about what x I choose, then I am in good shape, right? Because this, so for example, if x happens to be the median element or something, I am looking for 50th smallest element, and if x happens to be the median element, good. Either way, I get to throw away half the elements. Then I will be in a recurrence t of n by 2 plus order n, which will boil down to order n. Okay, so in particular, let's say if I pick a random element, okay, now we have to be very formally define what random means and do this analysis carefully, but let's go with their intuitive understanding of what a random element is. Suppose I have this n numbers, let's say this is of rank n by 4 and this is rank 3n by 4. So rank meaning an element's rank is an ith smallest element as rank I. Okay, that's the definition of I. Ith small. So median has rank n by 2. Okay. So let's say this is an element of rank n by 4 and this is an element of rank 3n by 4. Okay, I mean it need not be sitting here, it need not be sitting here, but just I picked up some elements. Okay. Now I pick a random element. That means I close my eyes, consult a random number generator, which I am told will give me equally likely any of the locations. What is the probability that that element will have rank between n by 4 and 3n by 4? Right? Because there are half the ranks are there. So which with probability at least half. Now if your x happens to be here, right? If x happens to be somewhere here, then regardless of which case you fall into, right? Either you will recurse on the left side or on the right side, you get to throw away at least how many elements? N by 4 elements, right? Because if x happens to be having rank somewhere in the middle, see the real bad case was x's rank was at the extreme, the smallest or the largest, then it was a bad case. But there are enough number of ranks in the middle that with good probability at least half, you will end up picking your x in this rank. And then when you do these comparisons and do your partitioning, either this gets thrown out or that gets thrown out. So at least some n over 4 elements gets thrown out. So it will be order n plus t of 3n by 4, which is a good thing. And that's going to happen with good probability. Okay, so this one can convert it into a good randomized algorithm. Okay, so we will, so if I say, so if x is chosen randomly, this gives order n in expectation. Okay. So this is a loaded term. At some point we'll get into formal way of talking about randomized algorithms and analyzing them. But you understand what does expectation means here? On the average. Average over what? All? What cases? What?
If we run this algorithm for so many times, average number of times it is run in order of n.
So average over all possible choices for x. Okay, because this is my random step here, right? If x happens to be the smallest, there is a running time. If x happens to be second smallest, there is a running time. You take all this running time and take the average, and that average will be linear. Okay, so in particular, if x pick a random element, because it's also a recursive algorithm, and the good thing should happen at every recursive step also, remember. It's not about just the top step. Okay, so randomized algorithms we will get into and we will do careful analysis later on. But for now, I will actually straight away go to a deterministic algorithm which tries and achieves this running time. Okay, so The point is to find a good x. Okay. After that, it's the same algorithm. We will do a partitioning with respect to s, count how many are smaller, how many are larger, and see which side to recurse, and we ensure that at least some good fraction is thrown out. That's the goal. Okay. But the goal is to find a good x. But before that, let me actually generalize this recurrence a little bit. Okay, so how do I, first of all, I mean, we expanded it and we showed it's linear time, but I told you how do I prove that this is linear time? I mean, I told you another way to prove it. By induction. Exactly, right? By induction, I can show that this is order n. Let's try and show it, right? I want to show that this whole thing is at most some Cn. So let's say this is some Dn, right? I want to show that this Tn is at most Cn for some constant C, right? Base case, you take your T of 1 and choose your C large enough so that your base case is satisfied. At the induction step, you're going to assume this for this smaller value of n. So what we'll have is at the induction step, T of n is equal to T of 7n by 8 plus D times n, which is less than or equal to, by induction, it's 7Cn by 8 plus Dn. Okay, because this is at most C times whatever sitting is in there, right? And what do I want this to be? The same constant C. So let's not, because we are trying to show Cn, right? So I want this to be at most Cn. This is what we want to prove, right? I want to prove that there is a constant C for which this is true. I can choose my C large enough, which will satisfy the base case, that I can get this to be true. Let's try and see what should be the condition for C. Well, we can simplify this. So what do I want C to be? So let's cancel out the n. Okay, I want C into 1 minus 7 by 8 should be greater than or equal to D. Right? So I want C to be greater than or equal to D by 1 by 8, which is equal to 8D. So choose your C greater than or equal to 8D, then you can prove this. Right? Is that clear what I did? Because all I did was I cancelled out this n. Okay. And I said this C, I took it common, C into 1 minus 7 by 8, the other side, I want it to be greater than or equal to D. D is fixed. D is a property of your algorithm. Algorithm took Dn steps. C is my choice. I am trying to come up with the C, right? So this tells you that if you choose your C greater than or equal to D by 1 by 8, then that C would satisfy this, and you can prove by induction. And you can see that why I want this to be strictly less than 1, right? It's playing a role here. Okay. All right. So now I'm going to just generalize this a little bit more and look at the following recurrence relation. The same idea will work. We'll have T of n is some T of n by B1 plus T of n by B2 plus O of n. Okay. So I have this two different, it's not same B, so it doesn't fit into our theorem we saw. But let's try and again prove by induction. We want this to be, and so the important thing was that this 7 by 8 was less than 1, right? So I will insist something like this here, 1 by B1 plus 1 by B2 is less than 1. Then I claim T of n is order. So what in linear time I've thrown away a fraction of elements the way I've been saying it. Here I might do multiple recursive subproblems, but still in linear time I have thrown away whatever 1 minus 1 by b1 plus 1 by b2 fraction is gone, but I have multiple subproblems. Okay. You can prove this along the same lines because what do I want to show at induction step? I will want to show that some Cn by b1 plus Cn by b2 plus dn, I want this to be less than or equal to Cn. Right? Very similar to what we went through. So let's cancel out n here. Then what do I want C to satisfy? C into 1 minus 1 by b1 minus 1 by b2 has to be greater than or equal to d. So C is greater than or equal to d by. Okay. So in particular, what I'm saying is if I have a recurrence which is T of n equal to T of n by 3 plus 3n by 4n by 7 plus order n. This is also will solve to linear time because this will be 7n by 21, this will be 12n by 21, so that's 19n by 21, strictly less than 1. Okay, that's what they say. Okay, so everybody with me now? So we started with this master theorem for recurrence. We identified one case where it's linear time, which will be like this. T of n is some linear time, you throw away a fraction of elements. And I'm just saying you can do a little bit more. In linear time, you actually throw away a fraction of elements, and the remaining thing you might have multiple subproblems, and even then the whole thing will solve to linear time. You can prove by induction. Okay, so that's the kind of thing I'm going to get to. And let's come back here. What is our goal now? To get a good x deterministically so that in linear time, either in linear time or I will have some recurrence like this, so that at the end of it, I end up throwing away at least a fraction of elements to recurse into. Okay, ready? Let's get to that. So, this is one of the slightly involved divide and conquer, but it's a very cute, nice, powerful application of divide and conquer. Okay, so this is step 1. Divide L into groups of size 5. Okay, so a picture would be let's assume n is a multiple of 5, otherwise there will be some 2 or 3 or 4 elements hanging around here, we can deal with that separately. Okay, so I take my entire list n, just the way it's appearing, I'm dividing it into groups of size 5. Find median of each group. Step 2. Okay, how do I find the median of each group? You can do whatever you want. It's a constant size. There are only 5 elements, sort them, find the median, do all kind of comparisons, and you just find the median. Okay, so this is the median. Let's say I picked some median of all these groups. So how many comparisons? How much time have I spent? Constant for each group. N by 5 into some constant. So it's order n, right? So if I say median of 5, we can 5 into 4 by 2, so it will be 10 comparisons. Even if you make all possible comparisons, it's if I choose 2, which is 10. into n by 5, so it's like 2n, way below 2n comparisons. Important thing is that's linear. Okay. Step 3, find the median of medians. Median of the medians recursively. And that is going to be my x. Right? The earlier algorithm I said pick an arbitrary x. It's not arbitrary anymore. It is this x, which is the median of the medians. How am I finding the median of the medians? Recursively. So how much time does it take for this step? Yes, because it's a recursive step. So you have to use your recurrence relation. So if T of n is the overall time, for this group, it's T of n by 5 because there are n by 5 elements for which you are finding the median. So this will be T of n by 5. Now compare x with all elements. And recurs appropriately. Okay, I'm going to just write this because I told you the details in the previous algorithm. So what is recurs appropriately meaning? You count how many elements are less than x. If it is exactly k minus 1, x is your answer. Otherwise, if it is more than k, you have to recurse for kth smallest element in this portion of that. And if there are less than k elements with x also, then go into the right side and find your kth smallest element. Okay, that's what I mean by recursive appropriately. The key thing is, earlier I could not give you a good bound because I don't know how much x will eliminate. It might in the worst case eliminate just only x and everybody else may be there. It gave us a recurrence T of n is 1 plus T of n minus or n plus T of n minus 1, that's n square. But now I am going to argue x is not some arbitrary x. I did all this careful pre-processing and I found x. So I am going to now argue you have actually thrown away a good fraction of elements. Let's see how many elements are we guaranteed to throw away. Okay, so here is my x which I found by this median of the medians, and I want to find out how many are definitely in both sides, right? If I can show that I will have at least this many elements here, so that it is not at the extreme. At least this many elements here, at least that many elements here, then I am in good shape. Can you tell me how many elements are definitely smaller than x? N by? T n by 3n by 3n by 10. Yes, okay. Does everyone see that? Why? Remember, this is a median of the medians. So that means if x was sitting here, at least n by 10 elements are in one side and n by 10 elements are in the other side, because there are only n by 5 elements and this is the middle element. So at least n by 10 are here and at least n by 10 are here. And for each element here, that itself was a median of 5 elements. So there are at least 2 more elements larger than that, 2 more elements smaller than that. So if you look at all those which are smaller than x, that will be n by 10. For each one of them another 2, so it will be 3n by 10 will be smaller than x. I don't know about the bigger elements, bigger than this guy, but it may or may not be smaller than x, that I don't know. But I know that anybody who is smaller than x, there are 2 smaller elements, they will also be smaller than x. So at least 3n by 10 elements are smaller than x. By the same token, at least 3n by 10 elements are larger than x because of the same reason. So this number is at least 3n by 10. So this number is at least 3n by 10. So, okay, comparing will take me n minus 1 comparisons. So now when I am recursing, how many elements will be there maximum? I don't know where I am recursing, which is 7n by 10, because at least 3n by 10 are thrown out, right? Because I know that, for all I know, maybe only 3n by 10 is larger than this and everybody else may be here and I may be recursing here or the other way. But whatever it is, wherever I am recursing, is left would be at most 7n by 10. Now my overall running time would be T of n is, here is an order n term, here is an order n term, plus T of n by 5 plus T of 7n by 10. Let's come here, I have an order n term, and for this whole thing to be linear, what do I need? I want this 1 by b1 plus 1 by b2 to be strictly less than 1. What is 1 by b1 here? 1 by 5, and this will be 7 by 10, right? I want 1 by 5 plus 7 by 10, which is 2 by 10 plus 7 by 10, 9 by 10, strictly less than 1. So this whole thing solves to linear. Okay, very clever algorithm. So the idea is, first of all, a good randomized linear time algorithm, which just says pick a random element, partition, recur. With good probability, you are not at the extreme. You are in the middle, you will do very well. Okay. How do I make it deterministic? Make sure you do some pre-processing so that you pick your x which is not at the extreme. And what is the pre-processing we do? We just make sure it's a median of a large number of elements so that at least that many elements are in this side and that side. And really you have to start from here if you think about it, because we had the master theorem which told us if I want a linear time, what kind of thing we want, a slight generalization, and that's what you get to get. So this is again a recurrence relation helping us to design an algorithm. Okay, so this is there are some 5 people associated with this: Bloom, Floyd, Pratt, Rivest, Tarjan. 4 out of 5 have actually won Turing Awards. Okay. Not for this work, but it required all these great minds to. This was a 1973 result, but it's one of the very classic, powerful application of divide and conquer, recurrence relations, and so on. So now you can go back and dissect this algorithm, right? Why did we divide it into groups of size 5? Okay, you want to try with 3, 7. Odd number is good because median is very well defined. But if I just go and change it to 3 and work it out, and 7 and work it out, and see, our goal was this, right? In particular, whatever I am recursing here, plus whatever I can guarantee thrown out and whatever is remaining, this fraction and that fraction should be strictly less than 1. So that would be an exercise. Groups of 3 or groups of 7 in step 1. Okay, you really understand the algorithm and the recursion and the analysis if you do these exercises. Plug it in and see what works. Okay. This is 1973, but there's been a lot of improvements in improving the constant, but it was nice to know that you can actually find the median without necessarily sorting the whole input. Okay. They also switched off for some reason. Okay, I'll spend 5 minutes setting up the next problem, which we can talk next time. Automatic alarm set when they are tired. Okay, otherwise we'll stop. Continue next time. So next time what I want to talk about is multiplying two numbers. N-digit numbers, I told you how to do it in n power log 3, but we can, set it up as a polynomial multiplication problem, and we'll see how we can do it in n log n using Fourier transforms. Okay, anyway, I was just going to wrap up. We will continue next time. Yeah. Okay. So you didn't get the exercise, okay? Okay. So let's discuss that. So the first step in the algorithm, I said divide into groups of size 5. And then we said find the median of each group. And third step was find the median of medians. And then the last step was compare all elements with x and recurse. And what we saw was the running time. This will be some at most 2n. This will be Tn by 5. This is n minus 1 comparisons. And here we argued it's 7n by 10. So my T of n is at most 2n plus n minus 1 plus T of n by 5 plus T of 7n by 10. Since this fraction, which is 1 by 5, which is 2 by 10, plus 7 by 10 is strictly less than 1, this whole thing solves to linear time. So my question was, instead of dividing to groups of size 5, suppose I did with groups of size 3 or groups of size 7, how would the analysis change? Does it necessarily give you a linear time solution or not? Okay, that's the exercise. Because then you will understand why all this median of medians and all that we did. Because a key thing is to figure out what happens to this number. How many are you able to definitely throw out? Because all other things will be very easy, but you need to see how much can you throw out at the if you picked your elements in smaller groups or larger groups. Okay. So does that answer the question? Is the exercise clear? Okay. Okay. Thank you. We'll see you next time.